Let's continue the graph of the series RLC circuit. Okay, please remember this graph. Okay, here is I is a current, this is omega, and then the shapes is the bell shapes, and then the parameters, which is the peak of this graph, is Vm divided by Vr, and then it's attenuate at 0.707, then the rest parameters. Okay, the omega naught you already learned, which is the resonant frequency. So here we are going to learn about the half power frequencies, is omega 1 and also omega 2. Okay, it's a very long formula to memorize, and however, we can summarize. If you obtain the value of the circuit is Q, the Q value is more than 10. What is a Q? Q is the quality factor. Okay, I write here again. If your circuit obtain the Q more or greater than 10, we can summarize this formula using omega 1 equals to omega naught minus omega naught minus B2, and then the next formula is omega 2 omega naught plus B divided by 2. If the Q is less than 10, then you need to use this formula. Alright, okay, I draw again the shapes of the graph, I versus omega. So here is our shape, and then we have this value is omega naught, here is omega 1, here is omega 2. This slide we are going to use a formula which is the highest power dissipated using this formula. So we are going to search about the power here, and then we are going to search, or we are going to calculate the power for half power frequency for this value. Next, we are going to learn about the Q. What is the Q? Q is the quality factors. So let's see this graph. We have the amplitude versus the omega naughts. The Q, we have a very narrow graph, and then we have a very broad graph. Is used for the selectivity filters or resonant, and then below here is the B. What is the B? B is the bandwidth. Okay, if you still remember this graph, we have I here, we have omega naught, we have omega 1, omega 2. So what is the B for this graph? B is the bandwidth, so omega 2 minus omega 1. We also can use this formula, depend on the questions. Okay, this is the formula I talk about. What happened when the Q is more or greater than 10. We're going to learn about the parallel RLC circuit. Let's say this figure. Okay, this figure we have all elements in parallel. We have the current source, we have the R, we have the L, and also C. So what is the admittance? Okay, admittance symbol is Y. Y actually have a very good relationship with the impedance. Y admittance is 1 inverse of the impedance. So the admittance for these circuits is given in this equation, and then another forms this equation, and then we change into another form, the real part and also the imaginary part. This is the real part and then imaginary part. Now we just take the imaginary part when, okay, the resonance will occur when the imaginary part is set to 0. So we just take this element and then sets to 0, then we obtain what is the resonant frequency. So if you look this formula is similar for the series of parallel circuits. Okay, this is a similar formula for the series of parallel circuits. Next, we are going to see the graph. The graph is here, is V, and then omega. Then the curve is similar, the normal pattern of graph, and then we have at the middle is the resonant frequency, and then we have the parameters of half frequency, omega 1 and also omega 2. So here the element says the current multiplied by R, and then it decreased to 0.707. Yeah, this is a very long formula. Okay, can you guess, is this a similar formula or the different formula with the series RLC circuits? Okay, now we are going to see what the formula for the bandwidth and also the Q. Okay, how we come out with this formula, I explain in series RLC circuits. Please see this formula, okay, this formula, and then this formula. Is it similar or different with series RLC circuits? Alright, so what happened when Q greater or equal than 10? We can summarize a very long half frequency formula just for this formula. Let's learn the application for the resonance circuit. For this example is AM radio receiver. Okay guys, series and parallel resonance circuits are commonly used radio and also TV receivers to tune in station and to separate the audio signal, okay, the audio signals, and also the radio frequency carrier wave, this one. The incoming amplitude modulated radio wave, maybe 1,000 or more, are received by this antenna. A resonance circuit or the band pass filter is needed to select just one of the incoming wave, because we have so many waves, so we need to select only one wave. The selected signal is weak and then is amplified in stages in order to generate the audible audio frequency wave. Thus, we have the radio frequency amplifier to amplify the selected broadcast signals. The intermediate frequency or IF amplifier to amplify an internally generated signal based on the RF signals. And then the audio amplifier go through a few stages, and then just to make sure the signal just to reach this loudspeaker, so as a user we can hear what is the radio. It's just one example, and then maybe you can search what others example used in the real application resonant by using internet.